Like real quick, I see like you can't be yourself properly.
Good afternoon. So before the class, I checked there were 11 submissions. Can I have one representative per group put up their hand? I just want to make sure all the groups have submitted, just one representative per group. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. Thank you. So I'll read your descriptions, and by Thursday you can expect an email from me. If you don't have an email by Friday, it means I'm okay. Okay. If there is a problem, I'll email you. If you don't hear from me, that means you're good to go. All right. So let's continue with discussing linear regression. Let's do this problem. Please write this down. And we are going to go through it in steps. And I just want to build on what we did last time, which is least squares regression. We also did linearization last time. Today, I want to increase the level of complexity a little bit by talking about what is the 95% confidence interval for the fit. This is also the same thing I asked you to look up as participation exercise for the last lecture. We're going to go through it today. Okay. So please write this down. And just by looking at the X and Y values, you can guess that this is not going to be linear, because the X value, if you plot this or if you look at this, there is no linear correspondence. How do you say there is no linear correspondence or linear trend in this data? How will you say that? How are you saying that? Yeah, how do you know?
The spacing between X and Y.
So you can try computing delta Y over delta X between each of these rows. And you can, if you find out that they are approximately the same value, that means it's linearly scaling. If this value keeps changing or increases rapidly, that obviously means nonlinear. So just to check here, if you look at the first row, I have 2.51 minus 0.14 divided by 2.0 minus 0.5. That's the first approximation for the slope. I'll call that like M1. And that is how much? 37. This is 2.37 divided by 1.5. That's about 1.8 times, something like that. And if I take the second and third row, I'll call that M2. That is 15.3 minus 2.51 divided by 5 minus 2. So that's 13.3, 12.8 divided by 3. It doesn't have to be super precise. This is about 4.6 times. And if you look at the third and fourth row, M3, I can say this is 63.71 minus 15.3 divided by 10 minus 5. So that's how much? 58, 48, 48, 48.4 divided by 5. That's about 9. So you can clearly see that the slope is continually increasing, which points to this data being nonlinear. So if you plot this data, Y and X, if it were a linear data set, it will look like this. But since the slope is increasing as X increases, this data would climb faster than the linear and would go something like this. Okay. I want to quickly show you this. Once you're done writing, I want to show you this on Excel just to show how the graph looks like. So if you're just given a data set like X and Y values and asked to develop a fit without even telling you whether it should be a linear fit, the first thing you should check is to check if the slope is approximately constant. Just pick any 3 or 4 random values, check the slope. If the slope turns out to be changing over the values of x, that means a linear fit is a poor choice to begin with. Okay, we might still be able to use the linear fitting by linearization. We'll get to that. So with your permission, I'm bringing the screen down. You're seeing this? So here is the data. X values, Y values. Okay, if I just plot X and Y, my curve looks like this. If the slope continuously increases, the linear fit is not good. If I take the log of X, if I take the logarithm of X and the logarithm of Y and plot those two, I get a perfect fit. I get almost a very good linear or a straight line. Now we are going to figure out how to evaluate the fit constants for this line. Not only that, what is a fit? We discussed this maybe 1 or 2 lectures ago. What is actually a fit? It is a summary of the data set. By using an equation for this line, we are effectively replacing this column of data. Now this column has only 4 lines of data, but it could have 400,000 lines. Okay, it could be a large data set. When you are replacing a finite amount of data with an equation, you are losing some information. What are you losing? What do you lose when you go from a table of data to an equation? The exact values, the actual values, right? So now you are trying to say, I will use an equation that describes this curve to functionally replace the data, right? So with me on that, it functionally replaces the data. When you functionally replace it, you are not going to be able to reproduce every single value. Like every prediction from the equation will not correlate exactly with the value in the original data set. You are with me on the second thread. You're functionally replacing, and there is always going to be some shifting around between the predicted and the actual. With me? Good. The 95% confidence interval, or the statistical fitting uncertainty, is essentially an estimate for how much that difference can be. Your linear fit is functionally replacing the data. There is deviation. The estimate of the deviation is the confidence interval. So we are going to see today how to do the fitting and how to estimate that confidence interval, which gives you the upper bound for how much error can you expect by using the fit equation instead of the original data. What's the biggest advantage of the fit equation? What's the biggest advantage of using a fit? It's compact. It replaces millions of lines of data with a single equation that has fewer parameters. Instead of million numbers, you just carry around 3 numbers or 4 numbers. Okay, so that convenience comes with an uncertainty, and we are going to figure out how to estimate that uncertainty. Okay, so I'll write this down. I know I've said a lot of thread and arguments. I'll write that down so you can also make a note of it. Before I write, any question at this point? So the philosophical arguments are something like this. A fit functionally replaces the original data, which could be 4 lines or 400,000 lines. It could be anything. The value calculated using the fit most probably will differ from the original y values to some degree, to some or varying degree. What I mean by that is, here are your data points. Let's say the line drawn through them is like this. This is the deviation we are talking about. The confidence interval also known as fitting uncertainty, or the confidence interval or uncertainty of the fit is typically an upper bound estimate for the difference between fit prediction or estimate and the actual or true value. True value for a given range of x, the independent variable. This establishes the data is not linear. So we need to linearize Can I erase what's on the left here? Okay, so I'm going to get rid of this because I need the space. So let's define x equal to natural log of x. So we call this nu x. And y equals natural log of y. We'll call it nu y. So in the exam, these numbers will be given to you. That is this column, and every other intermediate column will be given to you. We still have stuff to understand. Okay. So those values, I have it in my Excel sheet here. Sorry. Yes. Yes, that is to linearize. Not linear. So what we generally do is we try to calculate both log x and log y. In some combination, they'll come out to be linear. So if the original data follows a power law form, y equals axb, you take the log of both sides, ln a plus b ln x. We'll call this the nu x. We call this the nu y. So y equals, I'll call this a naught plus a1 times x. Okay, so this is power law. This is a power law fit which you linearize by taking both the log of x and y. Suppose you had an exponential law. Since you asked the question, we'll try to address different scenarios. Suppose you had an exponential law, which is y equals ae power bx. So ln y equals ln a plus b times x. So this we'll call y equals a naught plus a1 times x. So here the data is between x versus ln y, x versus ln y. Here it's ln x versus ln y. So this is an exponential. If it is an exponential law, we'll use ln y and x. It's already a logarithmic law. Which states ln y equals a plus bx. Something like that. Okay. No, wait, this is the same. Never mind. These two are usually very similar. So if you understand these two, we should be okay. So these numbers, does anybody have, or do you want me to tell? Minus 0.6932. Minus 1.9661. 0.6932. Is that correct? Oh yeah, 0.6932. 0.9203. 1.6094. 2.7279. 2.3026. And 4.1543. So I'll write it here. Y equal to AXB, which implies ln y equal to ln A plus B ln x, or y equals A naught plus A1 x, where A naught equal to logarithm of A and A1 equal to B. We'll keep this in memory. We'll need it. We'll come back to it. But right now, the goal is to figure out A naught and A1. So using least squares regression, how do we set up equations for A naught and A1? Do you remember? So here's my trick, the thing that I used to remember this. Y equal to A naught plus A1 x. Okay. Sum over all values once. So sigma y, I equals 1 to n equals A naught n plus A1 times sigma xi I equals 1 to n. Okay, so this gets you your first equation. For your second equation, multiply by x and then sum. So that is sigma xi yi I equals 1 to n times a naught summation I equals 1 to n xi plus a1 summation xi squared I equals 1 to n. That gets your second equation. In fact, this trick will even apply if you are doing polynomial regression. If you had x squared, x cubed, this trick works forever. Okay, so we'll use it towards the end of the class again.
What happens to the n?
N is the number of observations. So this is n. N equals 4. Okay, so you need these summation values. The sigma y, sigma x, sigma xy, sigma xi squared. That will be given to you in the exam, and I'm going to compute that now quickly for you. Okay. Here are the values. Sigma xi, sigma xi squared, sigma yi, sigma xi yi. Three point 9120, 9120, 5.8364. I'm sorry. 8364. Sigma xi squared 15.3039 and xi yi 15.9567. All of these will be given to you, and n equals 4. So now that you have two equations for a0 and a1, please go ahead and compute that and tell me, please. Two equations, two unknowns. I'll set it up for you. 4 a0 plus 3.9120 a1 equal to 5.8364, and then 3.9120 a0 plus 15.3039 a1 equal to 15.9567. Let's get a0 and a1. So everything I put a tick mark will be given in the exam. This one, the form of the linearization to use may or may not be given. Do we have even A naught? Yeah, please.
864.
5864. 5863. 0.5863.
8929.
8929. Okay. Is anyone else able to confirm that? Yeah. Okay, good. Okay, so A naught is 0.5863 and A1 is 0.892. So I'm just trying to create a fit equation here. Um, exclusive. All right. Let's do- Okay. So look up here, please. So you have your fit y equals A naught plus A1x. All right. What is our original goal? Our original goal is to understand what is the fit for the data of the form y equal to ax plus b. So now you go back and use this transformation to get back what is a naught, which is ln a, or a equals exponent of a naught, and a1 is equal to b, or b equals a1. So what is exponent of 0.58? 5863, and B1 is 0.8929. Okay, so now The question is, what is the 95% confidence on Y and subsequently Y, which is calculated as AX to the B? That is the question you want to answer first. Okay, so here are the steps. I'll give you time to write. Please look up. This is sort of important. So next to the Y, we'll write Y fit. This is equal to A naught plus A1 times X. Okay. So let's use these A naught and A1 values to compute the Y fit values. Can we do that? Can we do that? Minus 0.0326, 1.2052. Are we sure about these values? 2052, 2.02334, 0.0234, and 2.6423. Okay, I'm going to check these. Give me 1 second. So if I use Excel, I'm getting A1 to be 2.0387 and A naught to be minus 0.45348. Anybody else got these values? No? Okay. Okay. If I use these values, I get fit values that are matching exactly with this column. So I wonder why we are getting these values. They provide you the correct set of values. Okay, that's correct. Y squared seems to be fine. Okay, this needs to be checked, but for the rest of the class, let's move with these values. Okay, because I need to make my point. A naught and A1. Okay, so the fit values minus 1.9479, minus 1.9479, 0.8783, 0.8783, 2.7464, and 4.1595. 1595. So these need checking. Okay, look up please. So you can see there are minor differences between the fit value and the actual data. So step 1 is for us to calculate y I minus y fit of xi. Let's calculate the difference between these two. Okay, we are going to add that, calculate that here. We are just interested in the absolute value, so you don't have to worry about sign. So I need the difference between these two columns. Zero point zero one eight two. 0.0420, 0.0185, 0.0051, 5. Okay. Recall, we are still trying to see what are the steps to get the confidence interval. Okay. So we are going to calculate what is called as SEE, standard error estimate. That's defined as summation I equals 1 to n y fit of xi minus yi squared divided by nu, where nu equals n minus number of fit constants. And nu is called degrees of freedom. Whole thing square root. So SEE, standard error estimate, is like a standard deviation normalized by the system size, normalized by the degrees of freedom, and in this case n minus 2 for linear fit, which is of the form y equals a naught plus a1x, n minus 3 for a quadratic fit, which is y equals a naught plus a1x plus a2 x squared. What would it be for a fit that has, let's say, a third order polynomial? Third order polynomial that looks like a naught plus a1x plus a2 x squared plus a3 x cube. How many fit constants do we have? 4. So the degrees of freedom is always the total number of data points minus the number of fit constants for a cubic, and so on. Okay. So our confidence interval again is the t statistic for the degrees of freedom equals n minus 2 and a confidence level that we chose 0.05 times SEE divided by square root of n. So the breakdown is SEE accounts for variations in the data. The T statistic accounts for statistical variations when used for prediction. And square root of n accounts for system size or data size. More data makes it more reliable. Take a moment, please look up. I just want to make this important point here. What are the consequences of having a data set, let's say, is not really linear, but you forcibly using a linear fit? What is the consequence of that act? Your data is not at all linear. Let's say it looks scattered and there is no obvious pattern, but you still force a linear fit through. What is the consequence of that? Where will it show up?
Misrepresentation of data, a low confidence interval.
No. If you misrepresent, that is, if your fit is bad, it's a bad approximation of your data. It has no obvious reason why it should be used. If you use such a fit, where will that difference show up in the numbers? Where will that show up? You have this is data. You're not doing anything. This is your fit. You compute something. Where does the rubber hit the road? That is the end result. But I want you to point to me where exactly that number will first pop up in your calculations. Here, a lousy choice for a fit will show up as a larger deviation from the data. This is the column where if this column shoots up, it means it's a bad fit. If the column stays close to 0, it means it's a good fit or a reasonable fit. Okay, so the SEE directly accounts for poor choices in the fitting function. Not all data is supposed to be linear, and every data usually has some background physical pattern that must be followed. Let's say you ignore all those rules, all those considerations, and you still forcibly take a function. The consequence will show up as a high SEE. If the SEE is high, then your confidence interval scales with SEE. You will get a wider confidence interval or a larger uncertainty for using that fit. And vice versa. That is, if you choose a data set or a function that aptly describes your data, that will result in a smaller SEE and a smaller CI or a smaller uncertainty in using your fit equation. Okay. Any examples from your lab courses where you did fitting and use the fit constant as the quantity that's being measured? Anything that you can recall from fluids lab? Have you measured flow rate and pressure drop? No? Yes, no?
He lost possibilities.
Okay, I'll just make a quick example on how this may be used. All of you have taken fluids lab or fluids course. Can I take that? Taking it now, fluids course, okay, lab course. So think of an experiment where, let's say you have a tube and you mount a pressure transducer or a pressure, measure the pressure difference between 2 points in the tube. Okay, so you are recording delta P, and downstream here, let's say we have a flow meter. Okay, so you are having a valve here. Let's say you set the valve, you are setting flow rate. For a given flow rate, depending on the tube diameter and the length, you are going to have a certain pressure drop. And for those who have taken fluids theory, you know that the flow rate scales as pressure drop times or times d to the fourth divided by 128 mu. This is from flow theory, which relates flow rate with pressure drop and diameter of the tube and length of the section. Okay, how you would do this experiment in practice is you set the valve, you record a flow rate, and you note down the pressure drop. When you plot the data, you would have Q and delta P, so you would have different values. If it's all laminar flow and it's the same fluid, let's say water or air, you're going to fit a straight line, and the slope of the line is essentially equal to d to the fourth over L times 128 mu. So the slope can be used to get viscosity. So if your goal is to set up a measurement method for determining viscosity of a fluid by measuring the flow rate across a tube where it causes a pressure drop, you would need to know how to plot the data, how to fit a slope, and the measurement doesn't end there because you need to report viscosity in, let's say, units of Pascal second plus an uncertainty. So what you should be able to compute here is the uncertainty in the slope. Same thing when you do your projects. Let's say in my example, I showed you a project to do the flow rate through a nozzle. I'm going to plot the volume versus time, and I'm going to have several values. And then I'm going to fit them to get a straight line, and the slope will give me flow rate. And I also need to know the uncertainty in the flow rate. Okay, so far what we have seen is that if you have y equal to a naught plus a1x, you know how to get a naught and a1. Actually, we need to check that. But the uncertainty in y or the confidence interval in y is equal to the t statistic at nu equals n minus 2 degrees of freedom and alpha equals 0.05 times the standard error estimate divided by square root of n. This definitely won't appear in the exam because we are already in the second half of the course. No more statistics exam. Yay. But this is something you will probably use in your projects. Okay, that's why I wanted to talk about. Okay, now we move on to the next important thing. Uncertainty in A naught and uncertainty in A1. That's the next thing I want to discuss. So just to keep it in one place, SEE equal to summation I equals 1 to n yi minus y fit of xi squared divided by nu whole thing square root. So if you want some written material that goes with this, page 140 to 145 or 147, page 140 to 147 of posted handout on uncertainties. So this is on Canvas. This handout can be found and you can all find these equations there. So y equal to a naught plus a1x, uncertainty in a naught is SEE multiplied by 1 over sigma xi minus x mean squared equals 1 Sorry. X mean squared, where x mean equal to the average value of x. So in our case, it will be the average of these four values. So for our case, x will be 15, 17, 17.5 divided by 4 or 15.5 divided by 4, 4.375. Correct? Four point three seven. So in a given problem, A naught or A1 might have some physical interpretation. If you want the uncertainty in either of them, you use this formula for A naught and uncertainty in A1 equal to SEE multiplied by sigma x xi squared divided by n. I know these formulas don't look very pretty, but you'll probably put them in a MATLAB code or spreadsheet. You're going to have to handle them in the exam. Okay, last piece of the puzzle. Sadly, one more piece, then you can take your picture. Okay. So remember, we were originally having y equal to ax to the b lowercase, which got transformed as y equal to a naught plus a1x. And there is a relationship between a naught and the original a1. So a naught equal to logarithm of a, which means a equals exponent of a naught. This is really straightforward. You're just going to see an equation, but look up, please. If lowercase a, let's say it is some physical quantity that you actually care about, and a naught uppercase is an intermediate quantity which doesn't have a big picture meaning. Okay, what you really want is the uncertainty in a and not really a naught. So that would be the dependence of a on a naught multiplied by the uncertainty in a naught. So what is this? This will be exponent of a naught multiplied by the uncertainty in a naught. Uncertainty in a naught is this quantity. This quantity here is called sensitivity. Yeah, absolute value. So we don't care about the sign. In fact, what we typically do is to write this as the squared and then square root to denote it's absolutely positive. I'll rewrite that more clearly. A equals e power a naught, which means uncertainty in a naught is the derivative of a with respect to a naught multiplied by the uncertainty in a naught squared square root. So in this case, that's like writing e power a naught multiplied by the uncertainty in a naught. So this represents the tools I expect that you might need to crunch your data. That doesn't mean it's exhaustive, but whatever I presented here can be extended to more variables. Suppose you're doing a quadratic fit, not a linear. All these concepts will carry over there. It's all extendable. If you get there, it's a matter of sitting down and trying to think through and generalizing it further. So in the time we have, I try to present information that I think will be useful for number crunching. Okay. For your exams, we are still in module. This is module 4. For exam 2, module 4 is still game. We will still do fitting, linearization. We will still do uncertainty in the fit. We will not touch the uncertainty in fit constants. I think for an exam that's too much, but we'll still do 95% confidence interval on a fit. So that equation, this one will still be for the exam. This won't be on the test. So when you're practicing for the exam, especially what could appear on the exam, I would recommend looking at examples 4.8, 4.9, 4.10. So examples 4.8, 4.9, 4.10, and problems from the end of chapter 30 to 33. Problems 4.30, 4.33. All these to be referred in the handout. Okay. Yeah.
Say this sensitivity is the whole quantity.
This is sensitive. I'll rewrite that clearly. Thank you for asking. Sensitivity, which maybe in a measurements focused class we can talk about a little more. Sensitivity is partial A over partial A naught. That quantity is called sensitive. It is like a small change in A naught. How much will it change lowercase a? That ratio is called sensitivity. It's kind of a slope. Like if you change a little bit of this, how much the output will change. I still have to figure out why we got the wrong fit constants. If I find out, I'll let you know. So to close out this chapter, we'll do a few more examples, and on Thursday I'll move on to interpolation. Example 17.5 from the text. I'll show you the example. Example 17.5 from Chapra and Canal, 7th edition. That's page 474. Okay, so we are going to do quadratic fit or second order regression. Okay, I'm going to bring the screen. Don't worry about writing, it's an example. Solution is already in the book. Okay, fit a second order polynomial to the data in the first two columns of table 17.4. So here is table 17.4, x values, y values. Okay. In fact, for the exam, you can expect a table like this where the sum values are given and you'll need to do further steps using these numbers. So you're given x and y, okay, yi minus y bar whole squared, okay, and then what is this one? Quadratic least square. Okay. So if you see here in the graph, we have the data points, which are the original data. And first thing for us to understand is how to derive the equation for this line or how to derive the fit constants. Okay. For all polynomial fits, the method we saw for least square regression for a linear fit can be easily extended. I'll show you how. But so far the problem is how to derive this equation. Okay. So if you see here, this is your fit equation. And the goal is to solve for A0, A1, A2. For linear fit, what did we do? What exactly was done by generating two equations, or how did we generate two equations for the linear fit? So the mechanics works like this. For your linear fit, this is your equation, right? yi equals A0 plus A1 xi. And where I can vary from 1, 2, all the way to n. You understand what this is? This is just taking any value, any particular value of x and substituting it in the fit equation to make an equation that connects yi a0 plus a1 xi. Yeah. Okay. So what we did was to write to vary I to generate n instances and then sum it up. So what we did was to write sigma yi equals a0 times sigma 1 plus a1 sigma xi. That's how we got one equation. And how did we get the second equation? We took this first equation. Can I arbitrarily multiply throughout by xi? Is that okay? Will it generate a new equation if I just multiply by xi throughout? Is this a valid operation or not? What do you think? In general, if I just multiply through xi, multiply with xi throughout the equation, will that equation be linearly dependent or independent of the first equation? Will it be distinct or not of the first equation? How are you so sure? That is true only if you multiply by a known constant and the same constant for every equation. But what we are doing here is to take xi and multiplying it throughout, and xi can vary. That is, each value of x is different. You can't possibly have all of them to be the same value or linear multiples of those. So in general, this will result in a new equation that is independent. So we generated a second equation by writing xi yi equals a naught xi plus a1 xi squared. So we got two equations to solve for a naught and a1. We are going to apply the same logic for quadratic, cubic, any polynomial or any type of function. How will that work? So I write yi equals a naught plus a1 xi plus a2 xi squared. Sum ones, sigma yi equals a naught n plus a1 sigma xi plus a2 sigma xi squared. I need to generate a second set of independent equations, right? So I'm going to multiply this with xi yi equals a naught xi plus a1 xi squared plus a2 xi cube, and then sum that will give me a second equation for a naught, a1 and a2, and then I can repeat the same procedure xi squared, and I can write xi squared yi equals a naught times xi cube or xi squared plus a1 times xi cube plus a2 times xi to the fourth. So there are my three equations to solve for a naught, a1 and a2. Every remaining argument I made about standard error estimate, confidence interval, uncertainty in the fit constants, everything carries over. Only thing we have now added complexity is instead of just a linear, we now have a 3-parameter fit like a quadratic function. From here, what generalizations can you think of? Like, are these the only type of fit functions you can think of? Some of you might have taken finite element method. You have looked at various shape functions. What else can you think of as fit functions? Anybody taking system dynamics, doing Fourier analysis of time series data? No? Okay. What other? Okay, let me ask the question differently. Suppose I have some oscillatory data that looks like this. Okay, suppose I have data that looks oscillatory. It behaves like a sinusoid or a trigonometric function. In that case, I obviously don't want to do a polynomial equation. Polynomial equation is good for data that has some kind of monotonous increase or decrease, but this data obviously won't fit well with a polynomial function. So I want to look at a function that goes something like y equals a sine t or a sine bt plus c cos dt, something like that. So I want to solve for a, b, c, and e. These are my fit constants. All I want you to now tell me is you're not going to ever do this in this class, but how will you set up equations to solve for a, b, c, and e? What I did was here to sum over all the data I have once to generate one equation. That's a no-brainer. We can start there. I want to say if I have data that looks like time and y of time starting from, let's say, t1, t2 all the way to tn, I have y1, y2 all the way to yn. This could be like displacement data in your system dynamics lab. Okay. So the first thing I can do is I can write sigma yi equal to a times sine bt I plus c times cos. Actually, should not include this. I'll just put sine t and cos t to avoid confusion. Does that get me one equation for a and c? Does that get me one? Now, the simple question for you is how will you generate a second equation that's independent of this equation, that's distinct from this equation? Yeah.
Divide by sine.
You want to what?
You divide by sine. Simplify the terms.
So you want to divide this by sine. See, the problem with dividing with sine or cosine or trig functions is they can sometimes reach zero, infinity. That is sine zero is a possibility. So your numbers will blow up suddenly. The safe play is to take this equation, multiply both sides by time. It still is nonlinear because time t, if let's say you take sine t and t sine t, these two are linearly independent, which you can prove by t sine t divided by sine t equal to t. If this number were a single constant, it makes them linearly dependent. If this function is not constant in general, it makes them independent. So you will write yt equal to at sine t plus ct cosine t. So the second equation you want is sigma tiyi equal to a times ti sine ti plus c ti cos ti. What is the problem with this equation? I have assumed a sine t plus c cos t, which means I am telling there is only one possible frequency in this data. That may or may not be true. I might need to correct that by saying plus b sine 2t plus d cos 2t. So I'll stop here. What I'm essentially saying is you can develop or start by setting up fit functions as complex as needed to describe the data. And what you should really know as a skill is to how to set up independent equations that will help you evaluate these fitting constants. If you are able to set up different equations, you can do fits of any complexity or any number of fit parameters. Okay. To keep it clear for the exam, here's the important words. for the exam. We'll do linear fit. We'll do linearization. We'll do uncertainty in the fit. We'll do second order fit. And that's it. For the project, you'll need to worry about uncertainty in fit constants and understanding sensitivity. Sensitivity. And last thing, for knowledge sake, understanding how to generate independent equations. Independent equations to solve for fit constants. It could still mean I might be able to combine this with what we have as scope and try to get you some challenging question for the exam. So combining this and this is still possible if I try. Okay. So this wraps up the regression portion of module 4. We still have what is called as interpolation, which is a really minor topic. I really don't know why they still have it in the syllabus. I really think we don't need to learn it. It's so obvious. We'll quickly touch upon that on Thursday and move to the next topic or next month. Okay. So thank you.
I don't want to.